Hello everyone, this is Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College for Women, Nalgonda. In this present class, now I am going to discuss the topic Gauss Divergence Theorem. This is BSc Physics first year, first semester, Mechanics and Oscillations paper, the first unit syllabus. The plan of my talk is first we will discuss the topic Gauss Divergence Theorem statement. After that, we will prove the Gauss divergence theorem. Then we will solve the problems based on Gauss divergence theorem. Then lastly, we will see the conclusions. Yes. So the topic is Gauss divergence theorem. Gauss divergence theorem. Yes. So first, I'm explaining the statement. The normal surface integral, write all of you along with me. The normal surface integral of a vector field A bar over the boundary of closed surface over the boundary of closed surface S is equal to the volume integral of the divergence of a vector field over a volume V enclosed by that surface. This is the statement of Gauss divergence theorems. What I am saying, the normal surface integral of a vector field, A bar over the boundary of closed surface S is equal the volume integral of the divergence of a vector field over a volume V enclosed by that surface. So mathematically we express this as, or vectorially we express this as surface integral vector. What is that vector? A bar dot ds bar. This is the surface integral of the vector field in the closed surface S. That equals to volume integral of the divergence of a vector field. So divergence of A bar dv. Divergence of A bar dv. That equals to the volume integral. Divergence of A bar, we know what is that? Del bar dot A bar dv. Del bar dot A bar dv. This is the mathematical statement of Gauss divergence theorem. Mathematical expression for Gauss divergence theorem. Okay. Surface integral A bar dot ds bar equal to the volume integral of divergence of A bar dv. Right. So if you remember this expression, you can write the statement, sir. Surface integral of A bar dot ds bar means the normal surface integral of the vector field that equal to the volume integral of the divergence of that vector field. Okay, in that volume which is enclosed by the surface S. Right. So let us see the proofs. So the proof of Gauss divergence theorem. So for that, I will draw the figure. Along with me, all of you also draw the figure. Okay. X-axis, Y-axis, Z-axis, origin, right sir? Now, okay, let us consider a closed surface. Consider a closed surface. Yes, closed surface, capital S, enclosing the volume V. Enclosing the volume capital V set. Suppose that this volume is divided into very small infinitesimal volume element. Suppose that it is divided into a very small infinitesimal volume elements. Infinitesimal means very small. Infinitesimal volume elements. Each of volume V, small dv, each of volume small dv, okay, volume dv, all the sides along x, y, z axis are dx, dy, dz respectively. Okay. So what I'm saying? So we are considering the closed surface capital S that is occupying the volume V. The total volume is divided into very small number of small infinitesimal elements, each having the volume dV set. So in that, I consider a small volume element dV. This is the small volume element dV. Here, the sides along x-axis dx, along y-axis dy, along z-axis dz. I considered very small volume element dV that equal dx, dy, dz. So which is having the sides dx, dy, dz along x-axis, y-axis, z-axis respectively. So that is shown in the figure. Now, the value of the vector along the left face of this cube. This is the left face of the cube. This is left face. This is the right face of the cube along x-axis, right? The value of the vector along the x-axis at the left face of this cube, at the left face of this volume element here, ax. So here the coordinates x comma y comma z. Here the coordinates x plus dx, y plus dy, z plus dz. Okay. Here at this point x, y, z. Here x plus dx, y plus dy, z plus dz. Right, sir? So the side along the x-axis dx, that is written here. So now I'm writing step by step. Okay. So now, yes, look, sir. So what is that? The value of vector. The value of vector. The value of vector along x-axis. Along x-axis at left face. At left face is equal to Ax. Now, what would be the value of vector at the right face, at this face, at this face? Okay, so that is we will write the value of vector or x component of the vector along x-axis, at right face of volume element, at right face of small volume element is given by that equals to. So here ax plus the rate of change of ax with respect to dx, dou ax by dou x. This is for unit distance. From the left face to the right face, the distance is dx. From this face to this face is dx. So into dx, So at the left face x component, how much? Ax. So we are writing the component x component at the right face of this volume element. Ax plus the increment in x component dou x by dou x into dou x, dx. So therefore, the flux entering at the left face, along x-axis is given by that equals to the x component or the vector value, the value of the vector or the x component of the vector or the component of the vector at that point into ax into, so what is the area of this left face? Dy dz. So x component or the vector component into area of that face dy dz. So this represents the flux entering through this surface. Flux entering into the volume element through the surface dy dz. The area of this left face is dy dz. So how much flux entering into this volume element along x-axis? That is I am writing. This is equation 1. Okay. Similarly, the flux leaving from the right face or second face, from the right face of volume element along x-axis is given by that equals to. So what is the value of the vector? What is the value of the vector at the right face? This much. Okay. So that is that ax plus, you write that ax plus dou ax by dou x dx into area of that face. Area of that face, how much? Dy dz. Equation 2. So from equation 1, that is the entering flux. Equation 2 represents the leaving flux along x-axis. So what is the net flux along x-axis? Net flux along x-axis is equal to equation 2 minus 1. So this is this amount of flux entering, this amount of flux leaving cell. So now the next step we can write net flux along x-axis. Net flux along x-axis through the volume element is equal to this minus this. So here ax into dy dz plus dou x by dou x dx dy dz minus this. First term cancel. You will get dou ax by dou x dx dy dz equation 3. So similarly we can write net flux along y-axis, net flux through volume element volume element along y-axis. Along y-axis is given by, so what would be that? Dou ay by dou x dx dy dz. It is equation 4. So now similarly the net flux along z-axis, net flux through volume element dv, volume element along z-axis, along z-axis is equals to dou az by dou x dx dy dz. Okay, sir. This is equation 5. Along x-axis, the flux, the net flux dou x by dou x dx dy dz. Along y-axis, the net flux dou x y by dou x dx dy dz. Along z-axis, dou az by dou x dx dy dz. Therefore, total flux through the volume element, total flux through volume element in all directions through volume element dv, having the volume dv is equal to, we have to add these three equations: dou ax by dou x dx dy dz plus dou ay by dou ay by dou ax by dou ay by this is dou ay by dou y, dou az by dou z. Sorry, the net flux through the volume element along y-axis, dou ay by dou y dx dy dz. Net flux through the volume element along z-axis, dou az by dou z dx dy dz. Now the total flux through the volume element, dou x by dou x dx dy dz, that is I am taking common, plus dou ay by dou y plus dou az by dou z into, in all terms we have dx dy dz, that is common taken. This is the total flux through the volume element, through the volume element division. But we consider a closed surface S. So that closed surface S is enclosing the volume V. Therefore, total flux through the entire surface, total flux through a entire, through a volume V, okay, which is occupied by the closed surface S, is equal to, so what is that? Volume integral. So dou x by dou x plus dou ay by dou y plus dou az by dou z, we can write it as divergence of a bar. We know the Cartesian coordinates div a bar equal what we have. Del bar dot a bar equal dou x by dou x plus dou ay by dou y plus dou az by dou z. Okay, so that is, I'm writing one more step here. This is equals to I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z, right sir, dot I cap ax plus j cap ay plus k cap az into dx dy dz. So in the first bracket term, we can write like this. So this represents what? Del bar dot axi plus ayj plus azk, that is the vector field a bar. Dx dy dz is the volume of small volume element d. Del bar dot a bar d. It is equation 6. This is the flux through the volume element d. But we require the total flux through the entire volume v. Okay. Now the total flux through entire volume, volume capital V is given by, we have to integrate with the volume integration. Volume integral of this del bar dot A bar dV. It is equation 7. Equation 6 represents the total flux through the small volume element having the volume dV. Then the total flux through the total volume V, okay, enclosed by the surface, closed surface S is equal volume integral del bar dot A bar dV, or the volume integral divergence of A bar dV. Okay, now this is equation 7, sir. But according to the surface integration, the total flux through the closed surface, we can write it as, according to the surface integration, total flux, okay, the total flux through a closed surface, total flux through a closed surface, yes, which is enclosing the volume V, is equal to surface integral A bar dot ds bar, equation 8. Okay, in the vector field, we have taken a closed surface, yes, sir, that is occupying the volume V. Then the total flux through the boundary of the normal total flux through the boundary of the closed surface, yes, sir, according to the definition of surface integration, we write it as surface integral A bar dot ds bar. Here A bar dot ds bar is the flux through the small area element ds. Then the total flux through the entire surface is equal surface integral A bar dot ds bar. So here equation 7 and 8 represents the same. So then since equation 7 is equal to 8, so therefore conclusion, we can write the surface integral A bar dot ds bar is equal to the volume integral divergence of A bar dV. Divergence of A bar dV, or that equals to the volume integral del bar dot divergence of A bar. I am writing del bar dot A bar dV. Okay. Hence, the Gauss divergence theorem is proved. Okay. According to the equation 7, that is the total flux to the entire volume V. So that volume is what? That is the volume of the closed surface S. According to the surface integration, total flux to the closed surface S is equal to surface integral A bar dot dx bar. So equation 7 and 8 represents the same meaning, or giving the same value. Therefore, I'm equating 7 and 8. Therefore, surface integral A bar dot ds is equal divergence volume integral of divergence of A bar dv, that is called volume integral of del bar dot A bar dv. Hence, the Gauss divergence theorem is proved, sir. Okay, so this is the statement and the proof of Gauss divergence theorem. So based on this formula, we will solve the problems, right? How to solve the problems on the Gauss divergence theorem. Let us see. Okay. So let us solve the problems. The first problem, I'm writing. The surface S is enclosing. The surface S is enclosing a volume. The first problem. The surface capital S is enclosing a volume. Enclosing a volume V. Capital V. The force vector is equal to 2xi cap plus 3yj cap plus 3zk cap. Okay. Prove that the surface integral of f bar dot ds bar equals to a to b. Simple problems. So first, let us write the given vector, force vector. F bar is equals to, what is that? 2xi cap plus 3yj cap plus 3zk cap. This is the given force vector. Right, sir? Now, first you take the divergence of that. Divergence of F bar equal to dou by dou x of fx 2x plus dou by dou y of fy 3y plus dou by dou z of fz 3z equals to dou by dou x of 2x 2 plus dou by dou y of 3y 3 dou by dou z of 3z 3 equal to 8. According to Gauss divergence theorem, according to Gauss divergence theorem, so what is the statement? Gauss divergence theorem: surface integral f bar dot ds bar is equal to volume integral divergence of f bar dv. Just to have proved now. Avuna? So this is equal to, in the problem he's asking surface integral f bar dot ds bar. So that equal the volume integral. Okay. So that is I'm writing here. Surface integral f bar dot ds bar is equal to volume integral divergence of f bar dv. This is according to Gauss divergence theorem. I have written volume integral div f bar. We got 8 dv equal, you write 8 outside. The volume integral of dv is v. Answer v. So question: prove that surface integral f bar dot ds bar equal to 8. So that is we got here 8b. Right, sir? So in this model, you may expect the question. So one more problem, let us see. The next problem. Uh, if let S be a closed surface, let capital S be a closed surface, enclosing a volume V, enclosing a volume capital V. If the vector F bar is equal, if the vector capital F bar is equals to xi cap plus 3yj cap plus 2zk cap 2zk cap. Prove that, same model problem, prove that surface integral f bar dot ds bar is equals to 6v. Okay. First you write the given vector. What is the given vector? F bar is equals to xi cap plus 3yg cap plus 2zk cap. Okay. Now take div f bar, divergence of f bar equal dou by dou x of fx, that is here x component x, plus dou by dou y of fy, that is 3y here, plus dou by dou z of fz, 2z we have here, equal to 1 plus 3 plus 2 equal to 6. Now let us apply the Gauss divergence theorem. Surface integral f bar dot ds bar is equal to the volume integral divergence of f bar dv. So that is equals to the volume integral div f bar, we got 6 dv equal to 6 into integral of dv, answer 6. Hence the statement is true. Okay, so one more problem. The next problem is also very good problem. If capital F bar is equal to ax I cap plus by j cap plus cz k cap, where a, b, c are constants, okay, then prove that surface integral f bar dot n cap ds is equals to 4 by 3 pi into a plus b plus c into r cube for a spherical surface S. For a spherical surface S, where given r is the radius of the sphere. This is the problem. So here the force vector given f bar equal to axi cap plus a by j cap plus axi cap plus b by j cap plus cz k cap. First you write the given data. The force vector f bar equal to axi cap plus by j cap plus cz k cap. Okay, sir. Next you calculate the divergence of this force vector. Div f bar equal to, what is the formula? Dou by dou x of fx plus dou by dou y of f5 plus dou by dou z of fj. Dou by dou z of fx, ex we have here, plus dou by dou y of y component of the force vector. Here we have by, that is written. Dou by dou z of fz, cz. Okay.